and they changed it. All right. Am I on? Can you hear me? Is the mic on? Yes, maybe it's not. Oh, it's on now. Can you hear me now? Okay. Yes. So I'm just reviewing or stating the Langlands program in slightly different terms, because we learn different things by doing it in the two different possible ways of doing it, namely following his 7 questions, all of which, as I mentioned last time, it's an attempt by him to relate all of the questions to the first question that he stated. And the first question was about L functions, automorphic representations and L functions. So I mentioned last time that questions 4 and 5 were the ones that had to do with functoriality. And I mentioned that question 4 was about local functoriality. And it was that if rho, so this is where V is local. And it was where if rho V prime is an L homomorphism from the L group of this local group GV. GV is a completion of G to the L group of V. So that's a local L homomorphism. Is there a natural correspondence of their irreducible? So now we're not talking about automorphic representations, we're just talking about irreducible representations of these groups. And so is there a natural local correspondence pi V prime to pi V? At least this would be from the local representations, pi GV prime. That'd be the irreducible. We don't ask actually that they be unitary. We just ask that they, because one has to actually get out of the unitary category for some of these things. These are to be irreducible, maybe admissible. There's a couple of sort of general axioms that you put on the irreducible representations. And so in any case, his question is that, is there a correspondence? You recognize that as a kind of local analog of what we did, the way we described functoriality, such that, and I won't write it out again, but that preserves the L and epsilon factors. L of S, IV, RV equals its analog for G prime composed with rho. This would be for any representation RV, RV being any representation of the L group, of the local L group of G. So this would be for every R and for every psi, an additive character. Okay, so the L factors, the L functions, which Langlands, whose existence Langlands postulated in question 1, and the epsilon factors ditto. They are supposed to match. So this was vaguer than most of the questions. A correspondence. So he really does mean a correspondence. It's not a mapping. Really should be. A correspondence as opposed to a mapping. And it's not character, it's not written. Yes.
Sorry, just a very basic clarification. The epsilon factors are there to force this functional equation, right? Like
that's correct.
S equals epsilon times L over 1 minus S.
That's right.
So then what is special about this question? Like it seems like if you had L of S and if you had L of 1 minus S, you just take the quotient to get, and we'll get some kind of epsilon factor, right? Like the epsilon factor I should think of as the quotient of L of S by L of 1 minus S.
No, it's only a, don't want to say anything, but it's a quotient of global. It's the global version of it is going to be a quotient, but the local version is not.
Oh, so the global one I should always expect because it's just it's something I'm putting there to force a functional equation.
That's correct.
But the interesting thing is that I can break up that global thing, which is forcing a functional equation, into little pieces.
That's right. The little pieces are supposed to be uniquely characterized in some sense, but they're not as simple as you state it. And in fact, it's a funny business. The global L functions have a nice formula. The local L functions at the unramified places have this formula basically from the inverse of the characteristic polynomial of the Frobenius class, or the class CV. That's the global L functions. But if you have an unramified place, the global L functions are much simpler. And say in the case of GL2, they're 1 at a ramified place. So the global L functions don't amount to much at the ramified places, but yet the ramified places are more complicated, are supposed to be more complicated, and the complications are in the epsilon factors.
What made Rourke think of that?
I don't know, actually. That's a good question. I don't know. He apparently spent quite a bit of time trying to study. He spent quite a bit of time trying to study them, study Arden's work. But it's probably must be written up somewhere why he thought of them, or if indeed it was him that thought of them. I don't know. Maybe somebody before thought of them, but he's the guy that did the work on them, and then Langlands picked it up from that. So it really should be a correspondence, and it's actually not rigidly characterized. So unlike some of the questions, it's not a rigid definition of this. It's a sort of ad hoc definition. It's an intuitive definition. It can be rigidly characterized, but that came a little bit later, and I'll remark on this slightly again in a moment, but what did characterize them was a theory that came a little bit later, the so-called theory of endoscopy and L packets. And so there's a very nice way of characterizing what this local correspondence should be in terms of this later theory and in terms of what are known as L packets. Yeah, Melores.
Is these coincide, or they are just anonymous, or they have nothing to do like with root numbers, like for the leadership characters? They're also
no, they're the same thing. They're the same thing. I think if I understand or remember it correctly, the root number is like the value of the epsilon factor at a half. I think it's something. Is that correct? And I think Dwork called his papers root numbers. So yeah, it's the same business. they don't exist. They're all one. They're one in the case of the Riemann zeta function, but in case of Dirichlet characters, they're not one. And they're, I guess, for a long time in the past, they were known to be important. Okay, so then we have question 5. Langlands principle of global functoriality, which I've stated before, but I'll just state it. It'll be slightly different, stated slightly differently here. The notion of functoriality, as I've said a number of times, was not named at that point. At this point. So suppose that, so all of the questions at this point, after questions 2 and 3, are for quasi-split groups. Questions 2 and 3 were supposed to take care of groups that were not quasi-split. And so you could reduce everything to quasi-split groups. So suppose G prime and G are quasi-split. Groups over F. F's the global field. All of this, F is a global field. G's a group, quasi-split group over this global field. And so then we've got what we had before. When we were talking about functoriality, we have an L homomorphism between their L groups. So this is a global L homomorphism. Langlands had set up these questions. All of these questions came in the maybe last third of the paper. He spent the first 2/3 of it setting up what the L group was, which he didn't call an L group, and what an L homomorphism was, and all of these other things. Okay, so then the question was then, if pi prime is an automorphic representation of G prime A with local correspondence, pi v prime. This is the local correspondence postulated in question 4. Local correspondence pi v prime to pi v for every v. This is from question 4. Is pi v. So this is rather close to what we had described as functoriality earlier. Is this an automorphic representation of GA? So just to remind ourselves, this, let's see, just to remind ourselves, the slight difference between this and what we stated before. The earlier statement of functoriality was only for places, unramified places. V not in S. And it's more striking, I think. Certainly more elementary. It's easier to state, and it's more striking, I think, just for these unramified places, because they give very explicit information. These families, an unramified place gives a family of gives a semi-simple conjugacy class in the L group. So that's very concrete. These other things at the other places, it's less so. Well, this question, Langlands soon realized he 2 or 3 times complained in later articles that he wrote this paper too fast. It seems pretty good, I think, in retrospect, but he claimed he wrote it too fast and he made some mistakes. Or maybe mistakes is not quite the right word, but he stated some things that weren't as questions, which didn't always have a completely unambiguous yes answer, but it's a minor matter, really. But Langlands soon realized that this was a little bit too strong. Was a little too strong. Okay, so question 4 really is a correspondence as opposed to a function, a mapping. And then you've got the image of the correspondence, and the point is that not all representations I equals tensor V I V with pi V prime going to pi V for every V, right? So pi prime is supposed to be an automorphic representation of G prime. So you take then the supposed answer to question 4 for these local components, and Langlands asserts that or asks whether all these representations are automorphic, and they're not. It turns out that they're not. Not all representations in the image will be automorphic. Not so long after that, his later conjectural theory of endoscopy theory of endoscopy characterized the local image of the correspondence pi V prime pi V, and which products. It also characterized which products pi V are automorphic. So I'll say a little bit more about this, this theory of endoscopy, and which is a refinement of questions 4 and 5, is about you need the Weil groups to be able to describe it. Weil groups are a slight generalization of Galois, or generalization of Galois groups. So we'll say a little bit about that before we, in fact, I'll have to say some questions. The final two questions are about Weil groups. So questions 6 and 7 concern Weil groups. And what's known now is the local Langlands classification. Yes, I'll lead.
Before you move on, so this in this question, you say this product phi that you're getting is not. Does it have to be the corresponding automorphic? If it is automorphic, then does it have to be the corresponding automorphic representation for pi prime from before?
Oh, well, no. So pi prime is just any automorphic representation, and then this pi v prime to pi v, that's not a mapping. So pi v prime corresponds to a bunch of pi v's. So in that sense, every pi v is the image of the correspondence, the image from pi v prime of the correspondence. Pi v prime does not go to a unique pi v. It's a correspondence. It corresponds to a bunch of pi v's. It becomes a mapping if you phrase it a little bit more in a slightly more sophisticated way, which is what questions 6 and 7, well, they didn't exactly state it as is in that paper.
For each v, pi v in this question 6 and 7, conjecturally.
So I'll write it again more precisely, but the theory of local endoscopy describes this correspondence pi v prime to pi v explicitly. And what it does is it attaches to, it defines the notion of an L packet, which is a finite collection of representations pi v on the group G, or a finite collection of representations pi v prime on the group G prime. And the theory of endoscopy parametrizes the L packets. So what it is, it's very nice. Pi of G, capital Pi of G, that's the set of irreducible representations, local representations of GV. Pi of GV. The theory of endoscopy partitions that into a disjoint union of packets. And the packets are parametrized by so-called Langlands parameters, which are L homomorphisms from the Weil group into the L group. So we'll say what the Weil group is presently. But then you look, this is kind of like a Galois group. It's a little bit bigger than a Galois group. It's a locally compact group that gets mapped with a projection onto the Galois group. So it's just the sort of thing for which you can talk about an L homomorphism from this to this. And such things are always written as phi sub v and are called Langlands parameters, local Langlands parameters. And so pi g, the local so I guess I can say, if I've started this point, I can say what the conjectural, still not even known today in full generality, the conjectural local Langlands classification of pi of GV, local Langlands classification of the irreducible representations of the local group GV is as follows. It is a partition of pi GV into finite subsets called L packets. This is a subset, finite, subset of pi GV. And so these things are called, this is called a Langlands parameter, and this is called an L packet. And this is taken, a Langlands parameter is taken up to conjugacy in here, conjugacy by actually G hat, acting by conjugation here. So that gives an equivalence. And so equivalence classes of local Langlands parameters parameterize these finite subsets of pi GV, these finite subsets which are called local L packet. And what happens? This is a disjoint union of all of these local L packets, which in turn are parameterized by homomorphisms of the Weil group into GV. So do you want me to, I'll say it again, and ask me if it's not completely clear. The local Langlands classification is a classification of the irreducible representations, not necessarily unitary, the irreducible representations of GV. But what parameterizes them? What parameterizes them are these homomorphisms from the Weil group into here. And for every one of these local homomorphisms, there is, so part of this is still conjectural, there is supposed to be a finite subset of representations with the property that as pi v ranges over local Langlands parameters, the corresponding L packets are disjoint, and that their union is all of the representations. You look dubious. Does that seem plausible, or? Well, so I'll say more about it. And you'd say, well, okay, that's sort of that's at best a partial classification, because you're not saying what the L packets are. You're just saying that for every one of these homomorphisms, there's a finite collection of representations such that so-called L packet, such that the L packets are disjoint as pi varies, and such that their union is all of the representations. But that begs the question as to what the local L packets are. How do you classify the representations, which representations are in a given local L packet? And that's, of course, a natural and a good question. The theory of endoscopy answers that too. And it's a more subtle characterization, but it's in terms of geometric data, local, so-called local orbital integrals, and Langlands-Shellstead, so-called Langlands-Shellstead transfer factors. So I won't really talk too much about that, but the theory of endoscopy does give a classification of these local L packets. And then there's a global part of the theory of endoscopy that says, all right, if we accept the local Langlands classification at all primes V, and then, so then we take representations for each V, we take a representation from one of these L packets. So we can then take a global homomorphism V from the V group into the global L group, and that'll give you local homomorphisms by restricting it to the corresponding subgroup of the V group. And so if you have one of these global homomorphism of the V group into here, I'm not sure if this is the best way I want to say this, but if let's put it this way, if you have, forget about a global Langlands parameter for a moment, if you have, you've got this disjoint union of finite subsets of irreducible representations of G as V varies, and now you pick, for every V, you pick one representation, pi V, from the corresponding packet. I didn't think about this, so I hope I don't confuse matters further. Let me just say that, let me go back to what I was saying. So there's the notion of a global Langlands parameter, which maps to local Langlands parameters. And if you have a global Langlands parameter, and then you look at the local Langlands parameters, and then from each of those, you pick a representation pi V from the corresponding packet, when does the product of the pi V's become an automorphic representation of G? And the answer is quite precise, and it's in terms of the structure of the local L packets, and it's there's a precise answer to that. Okay, I'll try to set it up again a little bit later when we've talked about the V groups. So conjectures 6 and 7 concern V groups and the local classification of representations pi V and pi GV. So forget about the global stuff. What we're talking about, at least in question 6, is what, well, we want to make more precise what this correspondence is. The correspondence from question 4, the correspondence of representations pi V prime of the first group GV prime to representations pi V of the second group. So question 6 is directed at trying to make that local correspondence more exact and more precise. Okay, so I'm going to, I will do, I hope I can get this right. I think there's probably people here that know more about what I'm about to talk about than I do, but we first need a quick review of class field theory. V groups, class field theory, as I've mentioned, certainly in close to its present form, was around since the 1930s and the work of Artin. And V groups are things that are very closely tied. They're new groups. They're locally compact groups. They're related to Galois groups, but they are closely tied to class field theory. And I mean, this is abelian class field theory. Okay, so let me just review what the main assertions of local class field theory are. So let me write gamma, and we've been doing this regularly. I'm going to write that for the Galois group of any extension of fields, or any, let's say, finite Galois extension. E over F of fields. We're always working in characteristic 0. And let me write gamma sub E, gamma sub F, excuse me, for the inverse limit of over Galois, finite Galois extensions E of F of these finite Galois groups. So this is the Galois group. Galois F bar over F. I guess you have to fix an F bar to do this. There's it's a sort of a existential question as to whether there's not a unique F bar, but you choose an algebraic closure. So the Galois group F bar over F of an algebraic closure. F bar. And so this is it's like a p-adic group in some ways. This is a totally disconnected compact group. All right, so these, I mean, it's certainly fair game to be find this a little bit confusing, especially the first time one sees it. It was prescient at the time, but it was confusing, and it wasn't as refined as it became later with the theory of endoscopy. And it's things like that that I think may have discouraged people that were reading it. But we'll get through it. We'll figure it out. But in any case, so the this is this is it's a nuisance. I want to keep that one here. All right. Well, okay, so then there exists a continuous surjective map from the compact, totally disconnected Galois group to any of its finite, any one of these finite quotients. Galois extension E over F. And a class field theory talks about, it doesn't tell you about this full extension, that's the Langlands program at very least. But what class field theory tells you is about the maximal abelian extension of a given field F, the maximal extension which is Galois and for which the Galois group is abelian. So let's write then gamma F AB for the commutator quotient of the Galois group, gamma F, the totally disconnected Galois group. So that would be gamma of F modulo gamma F. I'll write C there. This would be the commutator subgroup. I mean, this all looks, if you sort of talk to a mathematician of the 19th century, this all looks very unpromising. So abstract and complicated, how could you get anything interesting out of this? But in any case, this is the Galois group. So this is the abelianization of this Galois group, or in other words, the Galois group of the maximal abelian extension. Let's say F bar abelian. And finally, one other thing that we want to write, if we would apply this to a local or a global field, F. So if F is local, in other words, p-adic, real or complex, I think we've used this notation before. We write CF simply for F star. Yeah, that works. It's confusing. This is very confusing. You get all these boards, right? And if F is global, we would write CF not for the global field F, but rather we want that to be bigger. We don't want it to be smaller than these local completions. The local CF for the local completions is F star, but CF for the global field is the adels. Actually, the multiplicative group of adels over F modulo F star. So this is what's known as the edel class group. which I believe was introduced by Chevrolet, maybe in the 40s. Anybody know? Was it in the 1940s? This is the very same Chevrolet that in the 1955 introduced finite, a huge family of finite simple groups. So maybe it was, in any case, he introduced that. And so class field theory classifies abelian extensions, maximal abelian extensions, or just abelian extensions, according to your taste, in terms of these groups here. So class field theory, I won't quite finish this today, but where have we got 56? So Vé groups, as I say, are very closely related to class field theory. So it's class field theory is both local class field theory. What are the maximal abelian extensions of a p-adic field? It's pretty easy for the reals and the complexes, but for the p-adics, it's more interesting. And then there's global. What are the maximal abelian extensions of a number field? So so local class field theory, if F is local, then there exists a natural, and the point is it's natural. It's not something that's non-canonical. A natural continuous surjective homomorphism from CF to F star there. That's the multiplicative group of the field. That's not too complicated. And however, it's a surjective homomorphism from that to the maximal abelian extension, to the Galois group of the maximal abelian extension. So that's wonderful if you're seeing it for the first time. So it's a homomorphism from the multiplicative group of F, namely F star. So so this is the Galois group of the maximal abelian extension. So it's continuous, surjective. So whatever it is, it's smaller than F star with kernel. The connected component of 1. Excuse me. The connected component of 1 in CF equals F star. So in other words, CF 0 is 1 if F is p-adic. It's radically easier if you've got the reals. It's equal to the it's equal to the multiplicative group of reals plus. So the positive real numbers, the multiplicative group of positive real numbers, if F is equal to R, and it's nothing at all if F is the complex numbers, it's just C star, if F equals C. So the case of the reals, if you haven't seen this before, the case of the reals and the C star is obvious. The maximal abelian extension of the maximal abelian extension of the group of the field C. Well, C is already algebraically closed, so it's just C itself. So this mapping, this group is 1. In other words, the kernel of this mapping is all of C star. For the reals, it's almost, there are not too many abelian extensions of the reals. There's just one, and it has Galois group Z mod 2Z for the reals. And so the kernel here is the positive, is the group of positive, multiplicative group of positive real numbers. So the multiplicative group of reals modulo the multiplicative group of positive real numbers is indeed just Z mod 2Z. And so that is indeed the Galois group of C over R, the maximal abelian extension of R. And p-adics, it's more interesting. And the p-adic field is in fact isomorphic in a very natural way, although making the connection is subtle. I've never really gotten completely used to it, but that's local class field theory. Very, very explicit. You've seen that, I guess, have you? Well, yeah, I mean, it's despite its apparent simplicity, reading through the proofs of, I've never really, I have to say, I've probably never really quite mastered it, but you can work with it without mastering it. And so we'll describe this and where you get the Weil groups next time. Actually, next time I am doing, I'll turn this off.